Welcome to phase 2 of our LLM series. We're now diving into the core mechanics. Today's topic tokenization and embeddings.
These might seem like technical details, but they're absolutely fundamental to how language models work.
Let's start with a basic question. Computers work with numbers, but language is made of words and characters. How do we bridge that gap?
That's where tokenization comes in. Tokenization is the process of breaking text into smaller units called tokens, and then converting those tokens into numbers.
The simplest approach would be to split on spaces and treat each word as a token. But this has problems.
Right. First, vocabulary size would be huge. There are hundreds of thousands of words in English alone. Second, you couldn't handle words you've never seen before. Third, many words are related run, running, runs, but this approach treats them as completely different.
So, modern tokenization uses subword tokenization. The most popular method is BPE or byte pair encoding.
BPE starts with individual characters as the initial vocabulary. Then it iteratively merges the most frequent pair of tokens to create new tokens.
For example, if E and R appear together often, you might merge them into ear, then ear and S might merge into ears, and so on.
You repeat this process until you reach your desired vocabulary size, typically 32,000 to 100,000 tokens.
The result is a vocabulary that includes individual characters, common subwords, and complete frequent words.
So running might be split into run and ning, while very common words like the would be single tokens.
This approach handles unknown words gracefully. Any word can be broken down into subword pieces that are in the vocabulary.
There are variants of BPE. Byte level BPE used in GPT models operates on bytes rather than characters. This makes it fully multilingual without special preprocessing.
Another popular method is sentence piece, which treats the text as a stream of Unicode characters and doesn't require pre tokenization into words.
Sentence piece is language agnostic and works well for languages like Chinese or Japanese where word boundaries aren't marked by spaces.
Word piece, used in BERT, is similar to BPE but uses a different criteria for merging tokens based on likelihood maximization.
Once you've tokenized the text, each token is assigned a unique integer ID from 0 to vocabulary size minus 1.
You also need special tokens. These are reserved tokens with specific meanings.
Common special tokens include BAS for beginning of sequence, EOS for end of sequence, PAD for padding shorter sequences to the same length in a batch, and sometimes SA for separating different segments.
Many models also use special tokens to mark different speakers or roles, like system, user, and assistant in conversational models.
Now that we have token IDs, we need to convert them into vectors that the neural network can process. This is where embeddings come in.
An embedding is a lookup table that maps each token ID to a dense vector of real numbers.
For example, if your embedding dimension is 768, then each of your 50,000 vocabulary tokens maps to a unique 768 dimensional vector.
These embedding vectors are learned during training. Initially, they're random, but the model learns to make them meaningful.
What makes them meaningful is that similar tokens end up with similar embedding vectors. Words that appear in similar contexts get similar representations.
This is based on the distributional hypothesis in linguistics. Words that appear in similar contexts tend to have similar meanings.
So, cat and dog would have relatively similar embeddings, while cat and democracy would be far apart in the embedding space.
The embedding dimension is a hyperparameter. Larger dimensions can capture more nuance but require more parameters and computation.
Typical values range from 256 for smaller models to 148 or more for very large models.
Now remember that transformers don't inherently understand position. We need to add positional information to the embeddings.
The original transformer used sinusoidal positional encodings, fixed mathematical functions that give each position a unique pattern.
These encodings are added to the token embeddings before the first transformer layer.
Many modern models use learned positional embeddings instead. Each position from 0 to maximum sequence length gets its own learnable vector.
More recently, there are methods like rope, rotary position embeddings that encode position directly into the attention mechanism using rotation matrices.
Rope has become very popular because it generalizes better to longer sequences than the model was trained on.
Another approach is AR-LIBI, or attention with linear biases. Instead of adding positional information to the embeddings, it adds a bias to the attention scores based on the distance between positions.
ALIBI is simple and very effective for extrapolating to longer sequences.
Let's talk about some practical considerations. Tokenization affects model behavior in subtle ways.
The granularity of tokenization matters. If words are split into many pieces, the model needs to learn to combine them. But if tokens are too coarse, you need a huge vocabulary.
Different tokenization can affect the model's ability to perform certain tasks. For instance, character level models are better at spelling tasks but worse at high level understanding.
There's also the issue of tokenization bias. Common words and concepts get their own tokens, while rare or non English words might be split into many pieces.
This can make the model less efficient or less effective for underrepresented languages and concepts.
Another consideration is packing and bucketing during training. You batch sequences of similar lengths together to minimize wasted computation on padding.
Long sequences are expensive because attention has quadratic complexity in sequence length. So there's often a maximum context length 2048, 4000 times 6 or 8192 tokens.
Some recent models can handle much longer context, 32K, 100K, or even millions of tokens using specialized attention mechanisms.
Now, beyond token embeddings, there are also sentence embeddings and document embeddings that represent entire sentences or documents as single vectors.
These are often created by pooling or averaging the token embeddings, or by using specialized models trained with contrastive loss to create meaningful sentence representations.
Sentence embeddings are useful for tasks like semantic search, where you want to find similar documents or passages.
The embedding space captures semantic meaning in a way that allows mathematical operations. You can measure similarity using cosine similarity or dot products.
There's even the famous word to vec example king, man, woman, queen. The arithmetic works because the embedding space has structure.
While that specific example is somewhat cherry picked, the general principle holds. Embeddings capture relationships and allow reasoning in vector space.
So, to summarize, tokenization converts text into discrete tokens using subword methods like BPE. Tokens are mapped to dense embedding vectors that are learned during training. Positional information is added through various encoding schemes, and the quality of tokenization and embeddings fundamentally affects model performance.
Next episode, we're diving into the heart of transformers, the attention mechanism explained in even more detail.
Thanks for listening.
Until next time, keep learning and stay curious about AI.